So next up, she'll introduce Dr. Bonner Newman, who's from TNO in the Netherlands. So Bonner is a program manager and a senior scientist working in exactly this field. So Bonner.
Check, check. Can everybody hear me? Okay. Very good. No problem. Well, so thank you, Ned, for the introduction. So I work in the Netherlands at the Applied Sciences Institute of the Netherlands called TNO. As you might recognize from my accent, I'm not actually Dutch. I'm American, and I wanted to say thank you to the. Oh, there we go. Is that better? Okay. Sorry about that. I should say thank you to the Digital Grid Futures Institute for allowing me to come here, because I think this is a great example of the fact that this question about transport is not just a local question, but it really is a global question. So I'm going to share with you what the Netherlands is doing, but it's really a global effort about making solar electric vehicles a reality. So this is, of course, what exemplifies this. This is the global adoption of EVs, and this is where it starts. So we are witnessing now a revolution in the transport market, that we're going to electrify the overall system for the reasons of climate change, energy independence, and other reasons as well that are motivating governments. At this moment, there are over 5 million electric vehicles worldwide. This includes plug-in hybrid electric vehicles. And there's over 3 million battery electric vehicles as of the end of 2018. So if we look at the Netherlands is a country of 17 million people with the area of approximately 2/3 the size of Tasmania, just to give you a little bit of perspective with that. And the Netherlands is actually a leading country when it comes to electric vehicle adoption. And so at this point in the Netherlands, as of the end of last year, there are now just over 200,000 electric vehicles, passenger cars, registered to drive on the roads in the Netherlands. And there's another 7,500 buses, electric trucks, delivery vans, scooters, and other types of vehicles. So why is this happening so quickly in the Netherlands? That will advance, yes. One of the reasons is because there are a lot of charge points. So we have over 50,000 public or semi-public charge points. And this is both from an investment from the government and also from private companies. So this means that for every electric vehicle on the road, there are approximately 4 charge points. And this means that people can actually they can easily buy an electric vehicle because they have plenty of places to charge it. And their distances between the charge points is not that significant. But for the world, we need to stop and ask ourselves how it is that people view vehicles. So by 2030, the Dutch, as well as many other European countries, have vowed to have all new vehicles be zero emission. Essentially, all new passenger cars will need to be electric. But there's 2 pieces to this problem. There's the supply, which in some ways you can regulate and you can ensure that all the cars that are for sale are electric. But there's also the demand, and you have to make people want to buy electric cars. So being an American, maybe I have this more than others, but for me, growing up, a car was more than just about getting from point A to point B. Cars are also about independence. They're about freedom from parents and the grid, for example, or the government. I mean, we have this idea of the open road in the United States and the idea of adventure. And I think the Australians have something similar in mind when they think about vehicles and their own personal transportation. And when you think about electric cars, you put a sign here for your next point to charge, and it changes this image a bit, because at some point you are going to be now dependent on this infrastructure or this line that attaches you to a certain place for a certain amount of time. Maybe it's an hour, if a fast charging system, maybe it's overnight. And so this is really what we need to overcome when it comes to the demand side of the equation. So fortunately, we're here at a university. The students have shown us what to do. So as Ned mentioned, there's the World Solar Challenge, and there's cars that have been developed for this, solar vehicles, and they've proven what is actually possible. And in Holland, even though we are a country with almost no sunshine, We have 4 teams that compete in the World Solar Challenge. These are the 3 teams that competed in the Challenger class. And perhaps more important for today, we have 1 team that also competes in the Cruiser class. And this is also where the SunSwift, which you saw outside, also competes. And so between Australia and the Netherlands, we are holding the top 2 positions in this race. So our students have really done something and shown us what is possible, but taking it from what they've done in the challenge to what people want to buy when it comes to their vehicles, that's the next step. So at TNO, one of the first things that we are doing is we are building an energy flow model for solar electric vehicles. And the idea here is that we want to take some real practical information, put it into a simulation, and really understand in many of the different complex ways how people might use these vehicles and what is the actual benefit. Because we can talk about extended range, but of course that's an average over the year. So what does it mean on a day-to-day basis? What does it mean about your planning and your need? What does it mean about your dependence on the government or on the grid? So in order to quantify that, we are using what we call charging moments. And so this is one of the outputs of our modeling here. And so a charging moment is when you need to stop driving and plug your car into the grid. Now, if you have a solar car and it's always charging, we're not calling that a charging moment. It's only when we're plugging into the wall. We also, of course, can talk about CO2 savings because, of course, that is a big motivator for why we want to electrify our vehicles. And, of course, the economic savings because you can't ignore economics. So in our model, we're putting in a bunch of different inputs. And what I'm going to show you is some of our first results on this. We've assumed a Nissan Leaf type of vehicle. Now, we at TNO, we have an entire unit of experts on electric vehicle powertrains. And so they have helped us by giving us, developing with us models of driver profiles and data from the real world about electric vehicle efficiencies in different road types, different driving styles, hills, no hills, etc. So we're using real world data about the electric vehicles, but using the Nissan Leaf as our example. And that has a nominal efficiency of 16 kilometers per kilowatt hour. Next, of course, is the solar yield model. So we have, I'll talk in a few minutes about some of the results we have about solar, putting solar actually on the car with what's available today. But for now, we've made it very simple, and we've said, if we can get 750 watts measured under standard test conditions onto the car, what does that mean for us? So we wanted to, because most of the cars that are out there that are commercial options for really powering the car are aiming somewhere towards 1,000 to 1,200 watts. So there will be caveats to that because of how is it installed? Is it on the sides? Is it curved? Is it this, what kind of shade is it underneath? But we're just saying, okay, if we can get 750 watts on there, what does that mean? And assuming that it's in the sun most of the time, that you have a driver who doesn't park in shade, for example. The next piece of information we need to include is also the battery size and the charge model. So at what low power rating do you actually need to start charging it? Are you willing to drive your battery down to 20% charge, or are you willing to drive your battery only down to 50% charge before you're willing to charge next? And the last bit is the location and the irradiance, which Ned just touched on. And that is the piece that we really do have to collect data for. And so that's one of the reasons I'm here at the UNSW, is to work with Ned and others to see if we can expand the collaboration to get more data from across the globe. In the Netherlands at this moment, we have built what we are calling the vehicle irradiance test setup. And you can see it here. It's quite clunky. It's not nearly as nice as the one that Ned is designing within his group here. But this one is somewhat over-engineered, but we're hoping that it will give us the sort of information we need to answer a number of different research questions, including making sure that we can use much less data to do the same thing, so validating some of our simpler models. So what we have is in each of the corners, there is an irradiance sensor. And then the module you see in the middle is actually not a module integrated with the car. It's just to power the system here. And then this has the ability to measure, it has a GPS unit and it also has temperature involved in it. So we're able to measure the velocity, the instantaneous velocity, and then in the middle plot the irradiance that each of the corners of the roof are seeing. as well as the temperature of the module and the irradiance sensors. You might notice here, and this is kind of nice to see what we can do with some of this data, that in the irradiance plot, there's a green line, and that green line is the local weather station compared to close to where the car is actually located during this day. So you can see it was used for a commute, driven in the morning and then driven in the evening. But what we see here, we notice this specific day because all of a sudden what we would have predicted if we looked at the local weather is that we would have gotten a lot more irradiance that day. But it turns out the person who was driving this parked it in the shade of a building, which is how people use their cars. And so this is really important information for us to see how people will really use it. So here's some of the output of our modeling that we've done, some initial modeling. So this is in Holland, again, a place with very little sunshine. And the top plot is with no PV, and the bottom plot is with PV. And there's a lot of information here, but the thing that you should look at and take away is these red circles. So every red circle that you see here is a charging moment. So in the top plot, you can see that approximately once a week, a little bit more than once a week, you need to plug your car in and charge. However, if you add PV to the car, and again, this is only these 750 watts, when it gets to be about May, you don't have to plug your car in anymore. And for the next 3 months, it's easy going. No more charging off the grid. And you can go from having 59 charging moments during the year to 33 charging moments during the year, according to these simulations. So now we can run that as a benefit summary for other places. We've done it for a couple places in Europe. So Maastricht is in the Netherlands. Madrid is in Spain, of course, and Stockholm in Sweden. So in Northern Europe, we can essentially save 40% of our charging moments, so you only have to charge it 60% of the times that you normally would. But in Madrid, which is potentially more like what you could do in Sydney or Australia, you can go from 62 charging moments in a year down to 20, as well as having about €350 a year savings and 400 kilograms of CO2 offset using this model. So the next step is, of course, trying to get the 750 watts on the car. So we are working with the company Lightyear in the Netherlands, which is one of the startup companies worldwide that is trying to make this a reality. They're actually a spin-out of the Solar World Challenge team Eindhoven. And about a year ago, we developed the first full-size car roof prototype. It had approximately 90% of the area was active with PV, with solar cells. We got better than 19% efficiency on that in our first Gen 1 prototype with lower efficiency cells, and greater than 86% cell to module performance. So as we increase the cell performance that we're going to use, we should be able to increase that efficiency as well. And so doing so, we should easily be able to get at least 1,000 watts on this vehicle using this technology, and potentially more if we increase the efficiency of the cells, as what Ned was describing. This design is now being integrated by Lightyear on their prototype car. This is the P0 on the road in San Francisco, California. And as you can see, they've done a very nice job of making it both aesthetic and very highly efficient. I can answer some questions about that later during the coffee hour if you're interested about the Lightyear vehicle in more detail. But of course, and there's also a number of other applications and companies that we're working with in the Netherlands to do this. There's a company called Trains, solar-powered trains, and these are kind of people movers, or they also make vans or these trains for last mile delivery inside cities. They are integrating crystalline silicon PV actually on their trains. There's also the company IM Efficiency, which Ned mentioned, and they're integrating PV on top of their trailer trucks in order to essentially for auxiliary power and refrigeration of goods. And then there's Picnic, which is actually one of these grocery delivery services. And they are also integrating PV onto their electric car. They have these little electric trucks that drive around delivering groceries. And they have now started putting PV on the top of these vehicles to prove applicability and feasibility. So I'd like to end on a bit of a personal note, because this is my son. He's about 10 months old, and he's just about to start walking. And I'd like to draw a parallel here, because what I realized when looking at my son is that when he is old enough to be driving cars. Solar on vehicles is going to be a reality. I'm not really sure what form it will be. It might be crystalline silicon, probably not. It might be multi-junctions, most likely. It may be something we haven't even thought of yet. But what I do know is that this technology is in its infancy. And we're really just taking our first steps right now with developing this technology and bringing it to the world. But I think we're really at the process of really picking up steam on it. And soon we're going to be running. And as we run, I think we'll be changing the world together. Thanks.